Okay, good morning, ladies and gentlemen. I hope midterm on Tuesday went well for all of you, or at least most of you. Some of you have asked when the grades would be posted. We are trying to grade all of the written portions, the short answer questions by this weekend, so that next week in your section you will be given back the your exams, including your Scantron scores and the short answer questions. You will be allowed to look at them in class in your section, and you will be allowed to request a regrade if you feel that your grade has not been, or your short essays have not been graded fairly, or what sometimes happens if you think the scores have not been added up correctly. Or the GSIs being physicists, sometimes you do make arithmetic mistakes. So the GSIs will explain this to you in section, that you're allowed to appeal your grade, although in this class it's relatively rare for us to either make mistakes or to actually give you reasons to believe we graded you unfairly. The single GSI grades all of the short answer questions. Well, actually we have 3 GSIs. One will grade a particular question so that everybody will be graded by the same person with the same rubric, which we will post by the end of the weekend on the B courses site, so it should be all fair. Having said that, if you have any concerns, please address them to your GSI in the section when your exams will be handed out to you next week. Do you have any other questions? If you have any other questions about any physics topics, again, this would be an opportunity to pause and reflect. What we'll do this week is I'm finishing off the discussion of the nuclear power, in particular the perhaps the most negative aspect of nuclear power, the 3 reactor accidents at the power plants. So we'll discuss the causes, we'll discuss the effects, and then we'll discuss perhaps what to do about nuclear power, in particular what to do about making it safer. And then we'll transition to electricity and magnetism. I have a few demonstrations here. We'll start on it towards the end of today's lecture, and then continue next week talking about applications of electricity that's actually everywhere in our life. So, if you don't have any pressing concerns or issues, let me go right ahead into the grim topic of reactor accidents. So before we parted last week, I talked to you about hazards, about the transportation of nuclear waste, the issues of nuclear storage, nuclear waste storage, and in particular the saga of the Yucca Mountain nuclear waste repository, which has been at this point cancelled, or at least marooned for some number of years. And we talked about other hazards that, of course, also have to be dealt with, that are not necessarily nuclear in nature. Chemical hazards also exist, and so when you're discussing safety of transportation of various hazardous materials, obviously both the nuclear waste has to be handled properly. The chemical materials that are significantly more frequent on our roads and railroads have to be obviously handled with care as well. In particular, the safety has to be also of concern to you as the future leaders. So, on the other hand, if you talk to general public, or if you think talk to your relatives, or if you think about safety of transportation systems yourself, or generally the safety of nuclear systems is much more, and concerns having to do with safety of nuclear systems, with the transportation of nuclear spent fuels, seem to be of a much greater concern to general public. And the reason for this is that I think one of the reasons for this is, one of the reasons is fear of unknown. Generally speaking, if you're sitting on an airplane is extremely safe, much safer than cars. Much fewer people die on an airplane, in airplane crashes than in car accidents. And yet, a lot of people have fear of flying. And this may have something to do with control. You are sitting somewhere at 30,000 feet in the air in a steel tube with, little windows, and, if anything goes wrong, you can fear of, plunging to inevitable death without any recourse for a passenger. If you are driving in the car, at least you have a feel of some control, right? Maybe you can steer around a accident site. Something similar, perhaps, has to do with radiation, in that radiation is invisible, generally. You don't see, you can see a mushroom cloud from a nuclear bomb, but from a nuclear reactor, if radiation leaks from Fukushima, or when the radiation leaked from Chernobyl, people didn't know, unless the government would announce at the time about the dangers. You don't see radioactivity, you don't smell radioactivity, despite what you may see in this recent Die Hard movie. It doesn't smell, it doesn't taste, unless the activity is extremely high. Whereas the chemical spills, at least you see a plume of chlorine smoke coming to you, maybe you can run, or maybe you have a gas mask. So there is perhaps, again, a psychological fear of an unknown, something that's invisible that may be coming to get you. So part of this class is to explain to you to get rid of, hopefully, this fear of an unknown, explain to you what's going on, explain to you what accidents have happened, what the causes are, how to prevent them in the future, and also for any particular accidents, and particularly about Chernobyl being the worst nuclear accident in the human history, what the actual impacts were on the population around the plant and elsewhere in the world. So here's the list. Nuclear power has existed, so nuclear reactors have operated since 1940s. The first nuclear reactor was built under the Chicago University Stadium by Enrico Fermi. It was hidden from view so that German spies perhaps wouldn't figure it out. 1942, the first nuclear chain reaction, actually the first nuclear chain reaction was obtained before that in the late 1930s. First reactor was being built in Chicago in 1942. So, what is it? 70 years ago. So in the last 70 years, there were 3 major nuclear accidents at commercial power plants. One in the US, 3 Mile Island in Pennsylvania, one in Soviet Union in Ukraine, Chernobyl, and one in Japan, Fukushima Daiichi nuclear power plant. In all 3 cases, the accidents had to do with lack of cooling power, lack of cooling water. In all 3 cases, the partial meltdown or partial destruction of the reactor was caused by overheating of the reactor core, caused by excess energy, excess heat delivered by the radioactive fuels, even after the reactors have been shut down, and the lack of circulating water that would take that energy, that would take that heat out of the reactor in time. So in all 3 cases, some fission products have been released in the environment and caused spread of radioactivity to various degrees, and we'll discuss all 3 of them now. So I guess the first, again, to remind you about the dangers, I think I said last week when we talked about nuclear power in principle is pollution-free. In theory, it's pollution-free. The working medium, the working gas in the nuclear power plants, the gas that actually generates, the gas that moves the turbines and generates electricity, is water vapor. So water vapor is not a pollution. Right? We have plenty of water in the oceans. So there's no additional greenhouse gases that are produced by these reactors. So if the entire reactor is enclosed and no radioactivity is allowed to escape, the nuclear power plants are producing power without any extra pollution in the atmosphere. One can think about them as being environmentally friendly. Of course, if an accident happens and the enclosure of the reactor core is broken, then radioactivity can escape in the atmosphere, and then you have to deal with the radioactive isotopes that can persist in the environment for years to come. And so that's another reason why nuclear safety and nuclear power plant accidents are of such a concern. That if there's an accident at a oil refinery, there have been recently accidents at releases of gases in the atmosphere at oil refineries. There's a bunch of refineries up in Contra Costa County, in Martinez. There are some refineries in Richmond, not that far from here. Every once in a while, they have releases of gases in the atmosphere, and the general public in Martinez, for example, is told to shelter in place. Close the doors, close the windows, sit at home, so that they wouldn't have to inhale possibly noxious gases. But then the wind comes in and the gases blow away and it's safe, sort of a few hours later. Radioactivity doesn't quite work this way, in the sense that radioactive contamination can persist for years to come because the radioactivity the isotopes that are released have a certain half-life, have a certain lifetime. So, for example, cesium and strontium, two of the most common long-lived radioactive isotopes, persist in the environment for 30 years or more, the half-life of about 30 years, and so the activity from the accident doesn't decay away very quickly. It decays away roughly by a factor of 2 every 30 years. Iodine is another common element that can be released in the atmosphere. Then there's also xenon gas that also has a relatively short lifetime. Iodine is one of the most common contaminants. It has a lifetime of 8 days. It behaves, iodine here in the periodic table is below bromide, below chlorine. It behaves like chlorine, so it can be dissolved in water. It basically behaves sort of like salt. Salt, natural salt, is sodium chloride, sodium chloride. So iodine can also be relatively easily dissolved in water. It can be also carried in the atmosphere by winds. It does decay fairly quickly, but before it decays, it can be absorbed by humans in the thyroid gland. Thyroid gland is designed to accumulate some amount of iodine for normal bodily functions. Radioactive iodine chemically behaves the same way as non-radioactive iodine. And so if there's an extra amount of radioactive iodine in the environment, thyroid gland may accumulate this. And then these radionuclides are sitting in your thyroid and decaying away roughly on average once every 8 days, so producing radioactive energy deposits. So to prevent exposure to this particular isotope of iodine, people near the sites of the accident in Fukushima, for example, or near Chernobyl, commonly given potassium iodide tablets. So this is the compound that contains potassium and iodine, the normal non-radioactive kind, obviously. And so the idea here is to saturate one thyroid gland with the non-radioactive iodine so that the radioactive iodine doesn't get absorbed. And that's the common prevention technique. And that's only useful if you're very near to the accident site, where the contamination is high enough for the absorption of radioactive iodine to be large, potentially, to be probable. If you're very far from the exposure site, doing this has potential side effects, both chemical, biological, and also radioactive. Potassium is slightly radioactive too, so in fact, ingesting potassium iodine without proper cause, it does in fact increases slightly your exposure to radioactivity. But this is, so near the reactor sites, typically this is the most dangerous isotope in the first few days, in the first weeks perhaps after the accident. And then long-term effects typically come from cesium and strontium. The fact that cesium-137 is a common isotope, it again sits in the periodic table here under sodium, so it behaves sort of also like salt. It can be dissolved in water and carried by ocean currents. Strontium-90, strontium is another rare earth metal, sits here right below calcium. It behaves chemically like calcium, so it can be absorbed in biological substances that are likely to have a lot of calcium in them. Bones, fish, for example, has absorbs calcium and therefore will absorb strontium as well and can accumulate it with some amounts. So when we talk about then effects of the radioactivity after a particular accident, there are two kinds of effects, and we discussed that last week. Acute radiation sickness, or ARS, that typically first responder workers can be subjected to, in particular first responder workers in Chernobyl that were exposed to very large amounts of radiation, fell sick of acute radiation sickness. However, general release of the radionuclides into the atmosphere exposes general public to a lower levels of radioactivity, not enough to cause acute radiation sickness, but enough to increase cancer rates. And so again, our most probable, common, mostly accepted theory about how much radiation increases the chances of cancer is this linear no threshold hypothesis. You were supposed to write about it on your midterm, that states that for every 2,500 rem, human rem, person rem of exposure, every 2,500 rem of exposure spread around some number of people would increase the cancer rates by 1. So if you have 2,500 rem spread around 2,500 people, one of them is likely to receive an extra cancer. If you spread it around 25,000 people, there will be one extra cancer in 25,000 people, etc. And what I wanted you to write down in this short answer question is, what are the limitations of this theory? And again, the limitations are such that the only data that this hypothesis is based on is from observation of humans exposed to radiation after Hiroshima and Nagasaki, when the exposure rates were very high, and there's no data at this very low exposure levels. So linear no-threshold hypothesis is somewhat conservative. It assumes that no amount of radiation is safe, and therefore it assumes largest possible number of extra cancers. But whether it's true or not for small exposures is at this point scientifically unclear. So when we talk about effects of radiation exposure after the Chernobyl accident or 3 Mile Island, and I will quote to you the number of perhaps extra cancer deaths in the entire world, all of those numbers are based primarily on this hypothesis. So the extrapolations based on Hiroshima and Nagasaki. Okay, so the first known nuclear accident, actually the first nuclear accident, well, there were two, not at the nuclear power plants, but at the scientific or the military facilities. The first nuclear accident actually was happened during the Manhattan Project, I think in Los Alamos, when the worker working on the assembly of the uranium, I think it was uranium and not plutonium, core accidentally put the two halves of the bomb together, starting the chain reaction. He was able to pull the pieces apart quickly, therefore preventing the explosion, but the worker died from radiation exposure to neutrons in the process. That was the first accident. Basically, something dropped. There was a safety pin that broke and caused the two halves of the bomb core to touch. The second accident was actually in the 1950s, 57, I believe, in a Russian facility used to enrich uranium and plutonium. The facility was called Mayak in the Ural Mountains, which used to be a secret facility. It actually still is. On the Google Maps, in fact, it's still kind of blanked out. If you look at the Google Earth or the satellite view of that area, there's a big white space there in the middle. That's this secret facility that still reprocesses spent nuclear fuel in Russia. And there was a radioactive spill there in 1957 that exposed over 50 people to high levels of radiation. Nothing was known about it at the time because it was a secret city. So only relatively recently information about this came to light. But these were effectively military facilities. There were 3 accidents at nuclear power plants, civilian facilities. And the first one was 3 Mile Island. Incidentally, one of the reasons perhaps it received so much widespread attention is the fact that this accident happened a few weeks after a movie about a potential disaster at nuclear power plant came out. It was called Chinese Syndrome, or China Syndrome. The movie was actually about some hypothetical nuclear power plant near Los Angeles. They filmed it actually at the thermal power plant, not a nuclear power plant. But so the sort of prototypical disaster movies that you should actually see. And then, in fact, a few months later, the disaster at 3 Mile Island, the accident at 3 Mile Island happened. I wouldn't qualify it as a disaster, it was an accident. And again, what happened at 3 Mile Island was a combination of multiple errors and multiple accidents, all happening in coincidence. So the original problem, the accident happened on the night shift, our shift. Somehow in every disaster scenario, if you watch, any, horror movies, bad things happen on night shifts, right? Chernobyl, the same thing. This happened on the night shift. There was a mechanical failure in the cooling system, in the secondary system of this nuclear power plant, the system that circulates water that is boiled and converted into steam and then runs the turbine. Actually, I think I probably have the picture of the reactor here. There it is. Oops. This is the picture of the pressurized water reactor of the type that are commonly used in the United States and of the type that was used in 3 Mile Island. It has 3 loops. The primary loop that cools the nuclear power plant, nuclear reactor. Secondary loop that boils water and moves the turbine. And then the third loop that then recondenses the vapor in the secondary loop. So what happened is that there was a valve stuck in the secondary loop in 3 Mile Island, and they decided to shut down the reactor automatically. So they followed the process called scram, which shuts the reactor down. There's a big button on the reactor panel that says scram. Push the button and shut the reactor down by inserting the control rods into the reactor core, control rods that have a large amount of material that absorbs neutrons very quickly, typically boron. So these control rods have a lot of boron element in it, and the borons absorb neutrons very efficiently, thereby removing neutrons from the reactor core, slowing the chain reaction to a halt. So this is exactly what followed in 3 Mile Island. In fact, you can Google why scram is called a scram. There is a, Wikipedia has an article about it. The claim, which probably is untrue, has to do with the, I forget what SCR, something safety control rod X-Men is what it allegedly stands for, which goes back to the 1942 reactor in Chicago, where somebody was supposed to shut down the reactor with an X. There was, additional cadmium and boron-loaded rods that were suspended on by a piece of rope, and somebody was supposed to cut the rope in case the automatic systems didn't work. So similar systems exist in every power plant where you can shut down the reactor by inserting control rods quickly. That happened in 3 Mile Island. But then when this happens, the power that the generators that circulate the water through the primary reactor core also shut down, and the backup generator is supposed to come on. So in this particular case, the backup system failed to come on. Some valve was also stuck, and the backup cooling power didn't. The backup generators that were supposed to run the water through the core of the power plant didn't come on. So no water was being pumped into reactor core. Reactor was still generating a lot of heat. So even though the primary chain reaction stopped, the radionuclides that accumulated in the reactor core were still decaying away. And when they decay away, they still generate heat in the megawatt range. And so if you don't circulate water through the reactor core, water is allowed and then starts to boil and eventually evaporates. So this was allowed to go on for a couple of hours. The operators on the night shift somehow didn't notice. The alarms were going off and were being ignored. That's not good. So by the time the operators actually caught on that something was going wrong, the significant part of the reactor was allowed to be exposed to air and overheated, and the core of the reactor partially melted. So what actually melted was the assemblies, the nuclear fuel assemblies that are the uranium pellets were being held in zirconium-cladded cylinders, and those cylinders partially melted. So that mess had to be cleaned up. There was partial release of radioactivity, primarily in the xenon, in the form of the xenon gas, and the krypton, radioactive xenon and radioactive krypton, was released in the atmosphere to relieve the pressure that was built up in the reactor core to prevent the actual chemical explosion. So about 15 curies of iodine was released, 2.5 megacuries of radioactive versions of the gases, xenon and krypton was released. And so about 2 million people in Pennsylvania around the nuclear power plant was exposed to small levels of radioactivity. How small? Well, by estimates, by measuring amount of radioactivity and observing how far around the nuclear power plant that radioactivity has spread, the Nuclear Regulatory Commission of the United States has estimated that about 2 million people has received on average 1.4 millirem of exposure. So then you can go back to this linear hypothesis and calculate how many extra cancers that exposure would have generated, assuming the linear no-threshold hypothesis, assuming that 1 millirem of radioactivity is as dangerous as any other amount of radioactivity. So multiply 2.5 by 1.4, you can estimate that roughly 1 extra cancer death was generated by exposure to this radioactivity, according to the LNT linear no-threshold hypothesis. There were actually probably more. There were no acute radiation sickness incidents, including by workers at the plant. Safety protocols were followed to clean up the mess. Radiation workers were not allowed to work on the reactor core longer than necessary to reduce the exposure to radiation. There were probably more than 1 death from panic that may have resulted from this accident. So most of the effect of this accident was in fact not biological, not economical, but perhaps psychological. And there was also a very large effect, obviously, on the nuclear industry that probably lost billions of dollars as a result of this incident. The biggest accident to date, hopefully ever, is the Chernobyl accident in Soviet Union. I remember it fairly well, maybe tell you some stories of my personal experience with it. I was 13 at the time. Chernobyl is in Ukraine, here. It's actually on the border between Ukraine and Belarus. That's now an independent country. In fact, in Soviet Union, most of the radiation exposure happened to be in Belarus that borders Ukraine. What happened in Chernobyl is probably even more tragic in that the accident was again a result of several failures and several incidents that all led to this catastrophe. And in some sense, the accident could have been prevented if everything if the operation of the plant was followed safety protocols. The accident was caused by A, not following protocols during a routine safety test. The accident happened during a safety test. And then B, an unfortunate design of the reactor that has this pathology in it. It had the so-called positive coefficient of reactivity. Again, let me show you the picture of the reactor. So Chernobyl reactor is of this type, RBMK, a relatively cheap, relatively high-powered nuclear power plant reactor designed for this sort of 2 purposes in mind. One is RBMK reactors were designed to be refueled while the reactor was in operation. So that helps with the efficiency of the operation of the reactor. It also helps withdraw spent nuclear fuel elements that have accumulated enough plutonium in it. So these reactors in the old days could be used to breed plutonium for nuclear weapons. So access to the reactor core was designed in, easy access to the reactor core was designed in. And so this reactor also used carbon, used graphite as moderator, and used water primarily for the cooling. And so the containment of this reactor was never under significant pressure, unlike these pressurized water reactors in the United States, which have the relatively strong tanks that surround the nuclear reactor core. The reactor in Chernobyl did not have to have a very strong containment system because no excess pressure was routinely designed to be present inside the reactor core. There was also no secondary containment in the building. Typically, most of the reactors in the United States have a primary containment system, so that's the steel tank that surrounds the core. It has the secondary, very strong containment structure, And in fact, this containment structure in the United States is designed to withstand impact by small airplanes, again, for the purposes of prevention of terrorism or accidents. They were actually originally designed for accidental impact by commercial, even small commercial aircraft. So the secondary containment structure is typically very sturdy and very strong, and that is designed to contain radioactive leaks in case of the breach to the primary containment structure. The RBMK reactors were thought to be safe. They thought to be designed for relatively routine low-pressure operations. They were designed to also be cheap. And so the secondary containment system was not designed to be very strong. It was basically just a brick or concrete building. It was not designed to withstand or to contain radioactive leaks because it was thought that the primary containment structure was sufficient. So that's the one design flaw of the reactor. And the secondary design flaw of this reactor is the fact that carbon, here, the graphite, is the primary moderator, and water that is used to cool the nuclear fuel doesn't act as a moderator, but rather absorbs neutrons. So it absorbs about 10% of the neutrons in the reactor core. So if this water is allowed to boil, the absorption of the neutrons decreases, more neutrons are produced, and therefore the reactor rate can speed up under certain conditions. This is very different from how the light water reactors operate, where the water is both the cooling medium and the moderator. If in the normal nuclear reactor, in the light water nuclear reactor, water is allowed to leak out or evaporate, reaction stops because neutrons are not slowed down and the extra neutrons do not produce additional fission. RBMK had this problems that under certain conditions, if water was allowed to boil, the nuclear reaction rate could actually speed up, so it had this so-called positive reactivity coefficient. That would only can be achieved when the reactor is operating at very low powers. So the manual for the RBMK reactors had in Cyrillic big red letters this statement. The reactors was designed to operate at about 3 gigawatt thermal power, or each core would produce roughly a gigawatt of electricity and about 3 gigawatt of thermal power, of heat. So that was the design, typical design power of about 3 gigawatt of heat was produced in these reactors, and it was written in the manual. These reactors were not to be operated below about 25% capacity, or about 700 megawatts. It was the smallest safe power level that these reactors were designed to operate. And everybody, the reactor designers, knew about it. They knew about this positive reactivity coefficient that could have been that condition could have been met at lower powers. So then what happened? The operators of the reactor actually knew about 3 Mile Island. So they knew what happened at 3 Mile Island was the failure of the backup generators that provided cooling power to the reactor core. So they knew that after the shutdown of the reactors, they knew that they needed secondary generators to come on and to pump water through the reactor core. And they had the secondary generators. And they ran tests where they would shut down the reactor and then turn on the emergency generators and see how quickly those emergency generators would come on. And it turned out that those emergency generators would come on roughly in a minute. So there was about a minute period between the reactor shutdown and the time when the water circulation was restored, and the reactor designers thought that was a little bit unsafe. They thought that period was too long to sustain cooling in the reactor core. They wanted to reduce that interval. And so somebody had a bright idea that, since every nuclear reactor has a turbine, right? So, normally you have this turbine, and it's a big, massive wheel that's spinning when steam is putting pressure on it. So somebody had the great idea that since this turbine is producing electricity, maybe after the reactor shutdown, it can still freewheel. If you add a little bit mass to it, it may have a lot of inertia. And so perhaps this generator can provide additional electricity for about a minute until the cooling, additional cooling pumps, additional backup pumps would come on. So they decided to test this idea. And how you test this idea? Well, you shut down the power plant, you shut down the reactor, and then you turn on still the generator that's now freewheeling, spinning still, and see if it can provide enough power to power the backup pumps. So they did this test a couple of times in the early 1980s, in 1982, in 1983, and once again in 1984, and each time that test failed. In other words, the generator did not produce enough power to actually power the pumps. So in 1986, they made modifications to the turbines, they made modifications to the test, and decided to test it one more time. The test was supposed to be done on April 25th, 1986, during the day shift, where the most experienced crew was around. Makes sense. So this is, summertime or close to summertime, I guess spring in Ukraine. It starts getting warm. Days are a little bit longer. This power plant was providing power for Kiev, which is about 100 kilometers away. Here's Chernobyl, here's Kiev. So they were going to shut down one core of the reactor during the daytime, perform this test, and then bring the power plant back on. During the day, some other thermal power plant in the Kiev area went offline. And so the electrical operators in Kiev called up the nuclear power plant and asked them to postpone the test. They wanted this Chernobyl power reactor to still be operational and provide electricity to people who are coming back from work at 5, 6 o'clock in the evening. So the power plant director decided, fine, we'll postpone the test until the swing shift, until the evening shift. So in the evening shift, there was some technical difficulties, and the test did not commence until about 12 midnight, exactly when the shift change happened. The most experienced operators have long left the power plant. They were scheduled on the day shift. They were scheduled to perform the test. Slightly less experienced crew was there during the evening. They were leaving too. The least experienced crew was there at night, and they were given the task of performing the test. The test didn't go as planned. The test, somehow the operators lowered the reactor power too much. The test was supposed to be performed at the thermal power of 700 megawatts, about a quarter of the design power. The operator somehow inserted the control rods too early, effectively shutting down the reactor to the thermal power of about 30 megawatts. So less than 1% or about 1% of the design power. And that was exactly the condition where the reactor could experience this positive feedback loop, where it could experience wild fluctuations in the thermal power and therefore large temperature fluctuations. The operators on shift didn't know this. The operators on the day shift knew about this. The night shift operators didn't. They somehow missed the big red Cyrillic letters that told them not to operate the power plant at the small power levels. And so they ran the reactor in this unsafe condition. It caused water in the reactor to boil, to evaporate. That speeded up the thermal process. When they realized that the reactor was running away, they tried to slam the control. Well, actually, several things happened. First, they realized the power was too low, so they pulled away all of the control rods out. That's also a mistake. Then, when they saw the positive reactivity coefficient, they saw the reactor started to heat up. They tried to slam the brakes again. And at that point, the reactor was already a little bit too hot. the control rods got stuck, so they couldn't insert them all the way in, and effectively the chain reaction happened. The water boiled in the reactor core, causing a steam explosion. By some estimates, the temperatures inside the reactor reached about 7,000 to 8,000 Kelvin or degrees C. At that temperature, as it turns out, another kind of fatal flaw in this typical reactor design, there's a reaction between zirconium and water that releases hydrogen. So that boiled water steam reacted with the zirconium cladding of the spent nuclear fuel, releasing hydrogen gas. That hydrogen gas exploded. And it got in contact with the hot elements of the reactor, and it destroyed the building. So what you see here is the end result, the destruction of this Unit 4 in the Chernobyl. The destruction was not a nuclear explosion, it was hydrogen explosion. Hydrogen gas exploded, leveling the building completely. In the process, the reactor core also opened up. About 3% of the uranium in the core was released in the atmosphere. So the amounts of radioactivity of about 5,000 picobecquerels. Pica is 10 to the 15. Becquerel is 1 radioactive decays per second. So the amount of radioactivity was about 10 to the 18, 1 with 18 zeros, decays per second. Huge amounts of radioactivity. So what are the impacts? Well, about 240 people have contracted the acute radiation sickness. What you see here is what the first responders saw. You know, when the reactor was destroyed, so there was fire. Operators obviously called the local fire department. Local firemen came. This is what they saw. This is a piece of graphite from the reactor core that were literally glowing with radiation. First responders were then reporting feeling kind of having some tingly feelings, you know, in particular in the face, from perhaps gamma rays. They reported tasting kind of metallic taste in their mouths, again, probably from dissociation of saliva into ions that conducts electricity, sort of similar to what you taste when you put a battery in your mouth, say a 9-volt battery. So the first responders they didn't actually know what they were dealing with. They were told to put out fire, and they went in and tried to put out fire. They would, you know, encounter literally a flaming piece of graphite, and they would pick it up and drop it somewhere in the bucket of water or off the roof of the reactor building, not knowing that they were exposing themselves to the lethal levels of radiation in the process. The crew that was on shift went in. They perished after a few weeks. The director of the power plant went in when he was called from home. The designer of this reactor committed suicide when he was under the investigation. So overall, there were about 31 deaths from radiation sickness. These were primarily emergency responders. There were 216 non-cancer and not ARS-related deaths. These are primarily heart attacks, stress-related casualties, and suicides. 130,000 people around the plant in the 50-kilometer radius around the plant were evacuated. In fact, even up to this point, so the area around the reactor, the town of Pripyat, is out of bounds. There were about 6,000 detected cases of thyroid cancer. In the aftermath of the incident, most of the thyroid cancers luckily is treatable with about 90% survival probability, but there are at least 6,000 documented cases of that disease. And then if you use the linear no threshold hypothesis, this graph, computing, according to Union of Concerned Scientists, an estimate of about 46 million RAM person exposure to the humans around the world would would have caused between 5 and 25,000 extra cancer rates. And the range here is because there's a large uncertainty on this number, primarily large uncertainty on the number of, on the actual amount of exposure. Soviet Union didn't handle the accident particularly well. The accident happened on April 20, well, night between 25th and 26th. The party leaders in Kiev were notified. The government in Moscow was notified. The decision was made not to announce about the accident, primarily to prevent the neighboring towns, in particular Kiev, that's only 100 kilometers away, prevent people in Kiev from panicking. That was the official party line. They also didn't want to let the world know about the accident. That was, I guess, embarrassing. The way the world has learned about the accident is from Sweden. There's a nuclear power plant in Sweden, which has, in fact, Sweden has a large number of nuclear power plants with exceptional safety records and safety regulations. Workers at the power plant noticed trace amounts of radiation, actually relatively significant amounts of radiation at their power plant. Their detectors tripped. So they thought they had a leak at their reactor. This was the reactor in the Forsmark town in Sweden. They went in to check. There were no leaks from the reactor, and they figured out that the extra radiation must be coming from the outside. I, at the time, lived near St. Petersburg, which at the time was called Leningrad. There's a nuclear physics institute in our town. We also have a nuclear reactor, a research reactor there, also with an exceptional safety controls. And some workers, one of the workers at the reactor, went running in the forest before coming into work. And then he came into work through the standard Geiger counter detector that's supposed to screen them for radioactivity when they're exiting the reactor building to make sure that they're not bringing contamination to their homes. He went through that screening procedure and detected radiation on his clothes, on the shoes coming into the reactor building, not from the outside. So then they went in and sampled areas around the institute, figuring out that most of the exposure must have come from a recent rain, and so must have been carried by winds, some from somewhere from the outside. So they notified the authorities as well. This was on April 29th or 30th. Next day is May 1st. May 1st was a big holiday in Soviet Union. May Day was a celebration of labor protests in Europe in the 19th and 20th century. Everybody was supposed to go and parade and demonstrate, wave red flags. The government didn't want to cancel May Day celebrations. They thought in Kiev, well, maybe we should, we're only 100 kilometers away, it's raining. This rain may be radioactive. Should we, reduce the exposure? And I decided, no, we cannot cancel the biggest communist event of the year. We'll just limit the parade from 4 hours to 2 hours. So nominally the parade takes 4 hours. They limited to 2 hours, so school children all went in, paraded in the rain, waved flags. Everybody had to go and celebrate. In my hometown, that's a little bit farther away, no limit was placed on the parade. It was still 4 hours. As it turns out, I was actually lucky. This was kind of a spring break. I was in the town of Lviv in Ukraine, which is some 600 kilometers west from Chernobyl. And as it turns out, the path of radioactive plume, as it was carried by prevailing winds, went northwest. So we kind of, escaped being hit. But I still remember that we were on the strip. Our teacher, at some point, somebody ran to her on May 2nd, whispered something in her ear, and she turned out to say, well, kids, we're all going into the train and we're going north. So we went north. There was some rain on the way, but we were sitting inside, so not much exposure to radioactivity happened. After I came home, my father, who worked at the Nuclear Physics Institute, told me to get into the shower right away, strip, give him the clothes, and he would, bag them and survey them for radioactivity, and nothing was detected. Another friend of mine, as it turns out, well, I didn't know him at the time, he was in St. Petersburg. He was on another summer trip in Kiev. He actually had to bury his shoes. They actually had large amounts of radioactivity on them. So a large number of people were exposed primarily in these areas. And the third accident that you have heard about now, it's on your memory, is Fukushima. Again, same thing, very similar accident to Chernobyl, very similar accident to 3 Mile Island, caused by a shutdown of cooling systems in the reactor core. In Fukushima Daiichi, the accident was caused by the electrical shutdown. There was a big earthquake of about magnitude 9 in near Tohoku in northern Japan. The reactors are actually designed to withstand large earthquakes. They're designed to withstand impact by airplanes. This reactor was designed to withstand magnitude 7 earthquake. There was more than magnitude 7 shaking on the reactor site, and the reactor survived without impact. The reactors were designed to withstand a tsunami, and indeed there was a tsunami after the earthquake. There was one fatal flaw in the design. So when the earthquake happened, electricity to the site tripped, power lines were destroyed, so emergency generators were supposed to come on and provide cooling power to the reactor core so that it could be safely shut down and maintained at a safe temperature. There were emergency generators, they were diesel operated. Problem was the reactor was sitting on the elevated area. It was designed to withstand a tsunami, and it did withstand the tsunami. Problem was the emergency power generators were sitting at the sea level, and they got flooded. So despite the fact that the reactor was designed to withstand a large tsunami, the reactor was designed to withstand a large earthquake, they had safety system, they somehow forgot that the safety systems could have been flooded. So the diesel generators that are supposed to provide backup power could not be turned on. They were flooded by a tsunami. That's what got destroyed. So the site had about a day worth of emergency batteries to run the electrical pumps, to run the electrical generators. They ran them for about a day. And after that, the cooling stopped. There were attempts to bring diesel fuel to the site, but again, the generators were flooded, so that didn't help. There were attempts to bring emergency generators, and that succeeded after a while. Obviously, access roads to the site were also significantly destroyed by an earthquake, so it was difficult to access the site. After a while, the Japanese authorities decided to flood the affected reactors with seawater, and that was a difficult decision. If you flood the reactors with seawater, the reactors are essentially destroyed. Seawater has enough elements in them to basically contaminate the reactor core, render it useless. So for a few days after the accident, the Japanese authorities were sort of trying to rescue the reactor without destroying it completely, and then after a while they resorted to flooding it with seawater to provide cooling. Nevertheless, for a couple of days, several reactor cores, there were units 1, 2, 3, 4, and then 5 and 6. Several reactor cores were exposed to air when the water was allowed to boil off. That caused overheating and partial release of radioactivity into the atmosphere. There was partial meltdown of the fuel elements that, especially after the reactors were flooded with seawater, allowed some radioactive contaminants to escape into the sea. So there's an estimate of the total of about 10 to the 17 becquerels of radioactive iodine and about 10 to the 16 becquerels of radioactive cesium that was released in the atmosphere and into the sea. Immediate vicinity of Fukushima was evacuated, Again, the Nuclear Regulatory Commission of Japan did not want to generate panic, especially in Tokyo, that could not possibly have been evacuated. So some information was not released promptly, and one can again discuss the wisdom of that. Nevertheless, people in the surrounding area were evacuated. There were no deaths that were directly attributed to radiation exposure. Emergency workers knew what they were doing. They actually called for volunteers to work and decontaminate the power plant, but even those volunteers were limited to their exposure, in terms of the exposure. So there were no deaths that could be directly attributed to radiation exposure, although some workers, I'm sure, received extra cancers. By the linear null threshold hypothesis, if one takes the amount of radiation released into the environment and multiplies by the linear null threshold hypothesis slope, one could estimate anywhere between 100 and 1,000 extra cancer deaths from this incident. And again, the uncertainty is a factor of 10 because it's difficult to estimate how much radiation was actually absorbed by humans. Luckily, at the time, the prevailing winds carried the radiation away from the populated areas. So instead of going south towards Tokyo, radiation went north. So that reduced the amount of exposure. In particular, the first hit was the winds were blowing northwest and not east towards the United States. Radiation was detected in the United States about a week later. About a week later, first rain came. This was March. I actually remember this also quite well. I went outside. I had a radiation detector. I had a sodium iodide detector in my lab. So I went outside. I collected about a cup of water, rainwater, put it in front of my detector to see if I could see traces of cesium-137 from this first rainfall that was thought to carry radioactive debris from Fukushima. I didn't see anything. The sensitivity of my detector was not good enough to actually observe these trace amounts of cesium or even iodine. I look for iodine as well. However, nuclear engineering department here at Berkeley actually had more sensitive detectors. They placed large water collection tents on top of the achievement hall. They literally would filter liters, multiple liters of waters and run them through their highly sensitive germanium detectors. And so they could actually observe trace amounts of radioactivity from Fukushima about a week after the accident. How much? They observed about 20 becquerels per liter of iodine-137 at the peak. This was the largest amount, and then this radioactivity decayed away very quickly. They observed about a slightly less than becquerel per liter of radioactivity of cesium-137. So how dangerous is this? Well, if you remember, I showed you this plot. So first of all, newspaper articles came about at about the same time. Signs of radioactivity from Fukushima are observed at Berkeley. Similar discoveries were made in Seattle. There's also a nuclear group in Seattle who observed trace amounts of radioactivity at the same time. And of course, what's important is to realize how much radioactivity was detected and how dangerous it is, not just to make statements that radioactivity was discovered and generate panic. I showed you that plot last week, is that if you buy a 1965 Bordeaux, or actually any wine from 1965, it has roughly a becquerel per liter radioactivity from cesium-137. This is the radioactivity accumulated in the air after the nuclear weapons tests. If you buy wine bottled in 1986, you will see cesium from Chernobyl at the level of about 0.2 becquerels per liter. So this amount, roughly becquerel per liter, is the highest amount of radioactivity in 1965 Bordeaux, is also similar to the highest amount of radioactivity detected in the rainwater in Berkeley. So if you drank a liter of rainwater, you would receive the same amount of radiation as a liter of Bordeaux. Personally, I would much rather drink Bordeaux. This, according to linear no threshold hypothesis, with all of its limitations, and the fact that we don't know whether low levels of radioactivity cause cancer or not, but assuming linear no threshold hypothesis, drinking a liter of rainwater at the time, or drinking a liter of Bordeaux from 1965, would increase your chance of cancer by about 4 times 10 to the minus 7. So that's about, what is it? It's about half a chance in a million. Now, that's a non-zero number. So if you spread this around a million people, if a million people drank a liter of water each, or drank a liter of Bordeaux, which probably doesn't exist in those quantities, there would be 1 extra cancer. Now, similar amounts actually are now being detected. There's a link to this Kelp Watch project at Berkeley. Nuclear engineering department professor Kai Vetter is collaborating with a professor in San Diego State to monitor levels of radioactivity in kelp. Kelp is the seaweed that grows in the water, and it turns out it's a great sponge. It absorbs everything. It absorbs every kind of cruds that exists in the ocean, so it's a good monitor of stuff in the water. And they're measuring amounts of radioactivity in kelp. They're measuring, in fact, with the sensitivity of roughly becquerel per kilogram, or slightly better. They haven't actually seen traces of Fukushima fallout in this kelp, but they have seen traces of radioactivity, perhaps from dumping in San Diego Bay of radioisotopes at small amounts, at becquerel per kilogram, roughly. So again, if you ate a kilogram of kelp, which I wouldn't do, that's a lot of sushi. So if you ate a kilogram of kelp, you would be increasing your radiation exposure again by roughly 1 count per second. Same amount as you would get after drinking a liter of 65 Bordeaux, which is much more pleasant, I'm sure. And that would increase your chances of receiving cancer by half in a million. So 1/2 extra cancer in a million. Of course, you have to then compare this risk to anything else that happens in real life. For example, if you were to drive to the coast for an hour to collect a kilogram of kelp and then drive for an hour back, your chances of getting killed during the trip in a car accident is 1 in a million, or roughly twice higher. So again, the traces amounts of radioactivity have been detected here. The traces amounts are extremely small. You have to decide for yourself how small is small. So what are the lessons learned after the nuclear disasters? So first of all, there are no absolutely safe technology. That's the fact of life. There's no absolutely safe reactors. We can minimize the dangers of the reactors by proper designs. All of the nuclear accidents that happened so far have happened because the reactors were allowed to overheat. So of the primary importance is the design of the safety systems that cool down the reactor cores. There's the new generation of reactors now being designed and built, the so-called AR-1000 reactors. This is the type of the reactors that the Nuclear Regulatory Commission of the United States has recently approved to be built in Georgia. In 2011, 3 years ago, now NRC approved 2 new power plants in Georgia, and they are of this type, the so-called Generation 3 nuclear power plant that has safety systems that provide cooling fed by gravity. It has a big water cooling tower. Like if you guys grew up, any of you grew up in the Midwest, right? You see cooling tower or water towers in every town, like big, tall towers that accumulate water. Something similar is built in the design of this power plant so that the water, cooling water, can be fed into the reactors by gravity without a need for extra pumps. So if something terrible happens and the emergency generators cannot come on, the additional safety is provided by gravity. There are multiple containment systems in these reactors, unlike Chernobyl. so that if the primary containment is broken, the radiation is then contained in the secondary containment. That, in fact, is what happened at 3 Mile Island. Contamination didn't leak out outside, except for the vapors that were released. So you can design the safety reactors. You have to train operators. You have to inspect the safety systems. You have to check that the operators have been trained properly and don't flunk their tests or don't cheat on their tests, like the recent story about the nuclear warheads officers in the United States Air Force that cheated on their tests. You have to make sure that the safety protocols are followed. But there are no guarantees. So at the same time, in the real worst disasters of Chernobyl type, the worst effects are psychological and economical. Psychological because they affect the great number of people, and the people who don't understand the numbers may worry, may have unfounded, perhaps, panic attacks and worries, and that has a psychological effect on the population. Again, if the information about Fukushima was broadcasted right away, and if you imagine a TV bulletin warning, radioactive plume from a nuclear reactor is coming towards Tokyo, what do you think would have happened? 10 million people would be trying to jump in their cars, into their trains or whatever, boats, and try to escape the city. Probably multiple deaths would have happened in the stampede. So the psychological effects are important. The effect on the economy also are significant. So what we can do is to reduce the risk. We can reduce the risk by designing the plants correctly, or, like some countries do, decide whether it's worthwhile to have nuclear power. And that, again, is a policy question. For example, Germany has decided, and Italy has decided, they will not have nuclear power plants in their countries. Instead, Germany is investing in solar power, and Italy is buying nuclear power from France. Well, Italy is buying electrical power from France. Well, and guess what? In France, 90% of electrical power is produced by nuclear power plants. France and Italy are neighbors. France and Germany are neighbors. So even though some countries have actually, and Japan as well, have divested from nuclear power, nuclear technology still exists in the neighboring countries, so it becomes a policy decision whether it's economically more feasible to develop your own nuclear technology and make it safe, or to divest from it, invest perhaps in other type of technology, and again, it becomes economical, political, or political-economical decision. But of the primary importance, if we are operating nuclear power plants, of primary importance is to design them well, design the most modern ones, and train the staff, and not let them operate the reactors outside of their design parameters, like what happened in Chernobyl. So there's some food for thought for you. After you've heard about nuclear power plants and nuclear accidents, what is better, nuclear power plant or the thermal power plant? Both of them can potentially produce health effects. Thermal power plant produce release contaminants in the air, pollutants, not even counting carbon dioxide that can cause global warming. Pollution is released in the atmosphere. People in China experience that every day. And by some estimates, there are hundreds of thousands of deaths associated with thermal power plants in China because of the increase in air pollution. So again, it becomes a policy decision of whether one risks operating nuclear power plants with their potential for accidents that happen rarely versus operating the thermal power plants that continuously produce health effects. What are the climate and trade-offs for nuclear versus thermal power? What you can do with nuclear waste, what you should do with nuclear waste, and what you can do with nuclear waste. This is something that your generation will have to face. In about 20 years, the storage facilities and nuclear power plants that are currently storing the spent nuclear fuel will run out of space. Your generation will have to decide what to do with them. Bury them right there and then, shut down the reactors and bury the waste, or collect the waste and store it in a safe facility somewhere underground, or reprocess this nuclear waste, for example, to allow it to decay quicker, or reprocess it to make more nuclear fuel. These are policy decisions. The cost and benefit of nuclear power versus other types of technologies is also an interesting question. And the questions of proliferation is also important. So I was going to make this Funding poll. I'll probably skip that now since we don't have time. Let me, in the next 5 minutes, show you a few more slides on yet another alternative set of technologies, and we'll talk about electricity and magnetism next week. So in addition to nuclear fission, which now exists commercially, there is a potential other nuclear reaction that powers the sun that can be potentially harvested to produce electricity here on Earth. It's called nuclear fission or fusion. So it's an alternative energy source. The nuclear fusion in the sun happens when the gravitational forces heat up the core of the sun so much that the hydrogen nuclei in the sun fuse together. And when the two hydrogen nuclei fuse together, forming a helium nucleus, or actually 4 hydrogens fuse together to form helium nucleus, energy is released. That process can only run efficiently in the very dense cores of stars. But here on Earth, we actually have run the reactions of this type, where you take a heavy nucleus of hydrogen called deuterium that exists in heavy water, combine it with a radioactive isotope of hydrogen called tritium, combine them together, producing a helium nucleus, a neutron, and about electron megavolts of energy per one reaction. So the amount of energy released is about 10 times larger per one reaction than the amount of energy released in a nuclear fission. And another great benefit of this reaction is that it produces very little pollution, very little radioactive waste. The only product is helium, and helium is great. You know, we use it in the kids' balloons. We also use helium to cool down superconducting magnets. It does produce neutrons, so one has to make sure that those neutrons do not activate materials of the around the reactor core, but the main byproduct is helium. There's a fundamental difficulty with this reaction in that the nuclei of hydrogen are positively charged, and we will discuss next week what happens when you combine 2 charged particles and bring them together. What happens is the positive elements repel. I'll demonstrate it a little bit better. You put 2 positive ions together, they try to repel from each other. You have to break that repulsion in order to make the fusion reaction happen. And so that usually happens when the nuclei are moving at high speeds or at high temperature. So that's why these reactions happen in the core of the sun, which has the very high temperatures of hundreds of thousands of degrees. And so in order to make this reaction happen, you need to heat up the gas to the temperatures of sometimes millions or hundreds of millions of degrees. And then you have to make sure that these neutrons somehow are either recycled or are not allowed to escape. So nuclear fusion is a promising technology, but it hasn't been demonstrated to work commercially yet, to produce self-sustained reactions. There are 2 facilities that are attempting to demonstrate a self-sustained fusion reaction. One is called ITER. That's a fusion reactor being built in Europe. It's a large multi-billion-dollar in Europe project that's being operated by multiple countries, or being built by multiple countries in France over the next 10 years or so. And there's another facility nearby here called NIF, National Ignition Facility, in Lawrence Livermore Lab. That's really is the site to be seen. It tries to run the nuclear fusion reaction by compressing the nuclear fuel by powerful lasers. It operates one of the most powerful lasers in the world, a petawatt laser. If you have a chance to tour this facility, tours are every once in a while arranged at Lawrence Livermore Lab in Livermore in the valley about an hour away. Take advantage of this. It's a extremely technologically challenging process, and I have just recently produced enough power from the fusion reaction that was equal to the amount of power being deposited by the laser beams. So the goal here is to produce electrical power by stimulating the fusion rates by powerful lasers. However, this process will probably take tens of years or so, so it's quite conceivable that if either ITER or NIF succeed, maybe in 50 years from now, we'll have nuclear fusion reactors, but again, your generation will have to be operating them. So let me stop here, and then I'll talk about electricity and magnetism next week. Thank you.